One of these days, Hawaii will burst at the seams.
A rockfall from a mountain. This is what most people would expect to see of a landslide, a pile of rocks at the foot of a cliff. But there's another kind of landslide, only recently understood. Dark, broken rock can pour like liquid, sweeping all before it, spreading like the fingers of a hand. For miles, it can run away. Early one morning in 1903, this Canadian mountain collapsed and ran out for 2 miles. It killed 70 people. Miners once came to the pioneer railroad town of Frank. They came to dig coal for the trains heading out west. But then the mountain fell, leaving a trail of devastation. And some miraculous escapes. This house was in the path of the slide, yet the families sleeping in it all survived. And the Spokane Flyer was flagged down by a survivor who leapt from rock to rock for over a mile to reach it. The mountain had literally been undermined, and the night shift dug itself out through a wall of broken rocks to find their homes had gone. 90 years later, geologists are still arguing over what really happened here. This is the steep outer edge of the landslide, leading up to a final high pile of rocks where it all ground to a halt. The scientific puzzle is how it traveled out so far.
13.5 degrees. Well, about 90 million tons of limestone fell from that mountainside in 1903. It fell down into the Crow's Nest Valley over there, about a vertical distance of 3,000 feet, and sped up this slope to where I'm standing now.
For over a mile, the rocks were coming up this hill.
Based upon interviews with the survivors of the Frank slide, the slide took about 100 seconds to reach the point where I'm standing now. This yields an average speed of about 75 to 100 miles per hour. When we reach the high velocities that we have here at the Frank slide, strange things happen. Debris moves up slopes, debris travels extremely large distances. They move through sharp bends at extremely rapid speeds, and in doing so form a super elevation at the surface of the debris, rather like a bobsled going through a bobsled run like this.
This is the story of how rocks can flow like water. In Australia, 2 geographers from the University of Wollongong were confronted by what looks like a completely different kind of puzzle.
Nice day for it.
All along the coast of New South Wales, Bob Taylor and Ted Bryant saw evidence of a force powerful enough to tear solid rocks apart.
Might go around this way, Ted.
It looked like damage done by water.
Bob, the more I look at this, I think the flow velocities are higher than what we've been thinking about. They're up around that 10 meter per second level.
If water travels at extremely high speed over rocks, it can form a vacuum. That can collapse. It can implode violently enough to carve out a groove like this. This groove and others like it along the coast are all lined up. They all point in the same direction. And whatever carved it out also threw 20-ton boulders around like pebbles.
But whatever the events, one or two, we're not talking about modern storm waves. No. These are far, far bigger.
It seemed that a tidal wave had struck. It could be traced inland, to where sand has been smeared into the clay. This could be dated. It all happened just over 100,000 years ago.
Something very, very big hit the coast. It wasn't recent, that was obvious. And even here in the big storm in 1974, which is the biggest storm along this coast in 90 years, none of these features were even washed over by waves. So we were talking about obviously something much, much larger than that. And what we could see was that these erosional features were all lining up with a wave approach from the northeast. Again, looking, if you will, across the Pacific over towards Hawaii.
4,000 miles away in Hawaii is another puzzle, set on the small private island of Lanai. Here the Pacific washes the shores of what was once a great volcano. High on the mountainside, rain has carved out a gully where volcanologist Jim Moore found a nagging problem: fragments of coral embedded in the rocks. And seashells. They've been found here at heights of over 1,000 feet above sea level. These are boulders of lava that came downhill from the old volcano, but they're all mixed with fragments of coral that were originally part of an undersea reef. How did they get uphill? Moore has roughly dated when they got here, again just over 100,000 years ago. So, did a giant wave sweep 1,000 feet up this island and cross the Pacific to Australia? If so, what caused it? Jim Moore's awkward questions were to overturn geological thinking. It all started 30 years ago in Hawaii. The volcanic Isle of Molokai has no great volcanoes. Where have they gone? Most geologists believe that they were gradually washed away by the weather. But Jim Moore realized that would have taken longer than the 2 million years since Molokai was formed. But Molokai does have 1,000-foot cliffs that drop 2 miles to the ocean floor. Was that where the volcanoes had gone? And on the next island, Oahu, half the volcano is missing. Could that too have collapsed in a giant landslide? There was no way for him to go 2 miles down and look for the missing mountains. But at the Hawaii Volcano Observatory, he saw an early map.
Hey Jim, I found that old map down in the basement. Oh, really? So we've got this thing still. This is that old Navy data that was the basis for this whole thing.
These were the U.S. Navy's deep-sea soundings in the 1960s.
Yeah, this is it.
Kind of
it sure
ancient
is.
and yellow, huh?
The first real breakthrough was when this Navy map was declassified in the early 60s. But one of the things that caught our eye is the fact that with the island of Molokai here, the north half seems to be missing. There's a train of debris that extends out a great distance to the north. Likewise with the island of Oahu, to the northeast, great trains of debris that extend toward the north, which appeared to be giant landslides. I did an analysis of this, satisfied myself that these were landslides on an enormous scale.
But in the 1960s, few geologists believed his idea of long run-out landslides underwater. They argued that his bump on the seabed was just a small dead volcano. And the Navy maps were not very good. There was no evidence there for his landsliding. There would be no funding for Moore's hypothesis for over 20 years. It took a stroke of international politics to change all that. In 1983, the United States extended its territorial waters by 200 nautical miles. To justify the vast increase around Hawaii, the seabed had to be properly mapped. Sailing from Honolulu, it was a British ship, Farnella, that did the job, with the help of new British equipment called Gloria, geological, long-range, inclined Aztec. Its signal was bounced off the seabed. The image is black for thick, flat sediments and white where it reflects from rock, to create a rather more reliable map of America's ocean floor. For the scientists, it was a revelation. It confirmed that Jim Moore's original 2 landslides were real. But it also showed that there were many more, at least 17, and all around the islands. By dredging, they brought up samples that dated back 100,000 years. Here was the power that could have created a tidal wave.
And very likely the rapid movement of a landslide like this could have produced the wave deposits of the sort that we saw on the island of Lanai.
On the latest seafloor map, from the west coast of the Big Island, the landslide carved out a path where huge blocks were carried out to sea. Such a force would have generated a tidal wave big enough to wash coral high up the hills of Lanai and sweep across the Pacific to Australia. On land, the violence of a run-out landslide was finally accepted at Mount St. Helens. On the American mainland, this was the mountain before it erupted in 1980. Early signs of activity, with 2 new craters, had drawn Jim Moore and many other geologists to the volcano.
I began working on St. Helens more than a month before the actual catastrophic eruption. We set up triangulation points. We were making measurements showing that the whole north side of the volcano was moving at a rate of more than a meter per day. We were monitoring it closely. We had a feeling that very likely it would break loose. We did not anticipate the explosion, the gigantic explosion. Fortunately, I did not happen to be there that day. On May 18th, that landslide tore loose and moved out 22 kilometers. Of that landslide unweighted the top of the volcano, depressurized the volcanic system, and that is what triggered the gigantic blast. It devastated such a broad area over the north side of the volcano and killed most of the casualties. We did not expect it would be that big.
Moore returned to the mountain to reconstruct a detailed chronology, to confirm the astonishing speed of that event. Without the photographs, few would have realized that the landslide came first, that it was already running before the explosion. It was far bigger and had run further and faster than geologists could have imagined. And it became a turning point in the history of geology. After St. Helens, no geologist could again question the reality of long run-out landslides. But it left wide open the question of how they work. How can falling rock go so fast and so far? The first slide to be studied scientifically was at a village called Elm in Switzerland. In 1881, it was also the first to be recorded by photography. Some of the villagers tried to outrun the landslide, but it was too fast. 116 died. Cows and dogs that fled to the side escaped. One house was lifted up, carried along, and dropped. The people inside, celebrating a baptism, were unharmed. The biggest rock still lies where the landslide carried it. Switzerland's leading landslide geologist, Ken Su from China, has uncovered the painstaking study originally made 100 years ago. It describes how rocks above a slate mine had already been falling several hours before.
It was a Sunday afternoon, and it was raining just like today. Now, then it has been falling all morning rocks, and another big rock fell down in the afternoon. And the escarpment is right up there. And it was observed by teacher Reese, and he lived in that schoolhouse over there. And from this position in the schoolhouse, he can watch the whole drama. First, he saw it looks like kind of a herd of sheep galloping down the slope, and then very suddenly it fell down and it hit this platform on the quarry there, and then broke down and looks like a waterfall. And the branch went up about 300 feet up to this hillside. But the main part of the slide, it has a big stream of rock debris and went 2.5 kilometers down the valley. So I was a schoolboy, and he was here when the whole thing came down. So he started to run towards the village. He ran this distance. Afterwards, he measures is 40 seconds. So 40 seconds, it come from here all the way down to the valley to this end. That's about 120 miles an hour. There was one old man in that house, and he was at the end of the scene, so he was noticing all the rocks are flowing past him. So he was buried in this debris up to his shoulder, but he wasn't killed. The whole thing stopped.
There's a long run-out landslide every 100 years or so in the European Alps alone. Around the world, every 10 years. Over geological time, the number is untold, but many still not recognized. The geological evidence is a pile of broken rocks that's in the wrong place. But they've often been misclassified, because geologists couldn't imagine how they got there.
Well, the problem with these long run-out landslides is they go too far. We kind of expect normal landslides, the debris would run out a distance horizontally about equal to the distance of its vertical fall. Many of these long run-out landslides run out 10 to 100 times the distance that they've fallen vertically, and that's very difficult to understand on the basis of ordinary measurements.
The Frank slide stopped only when it was heading back uphill.
The debris moved a lot further up this valley than would be expected if the material was acting like a purely frictional material. If you look at the tailor slopes over there beneath the scar, the angle of those slopes is about 35 degrees.
There's a pile lying at the normal angle for fallen rocks, but the rest shifted into higher gear.
The excess travel distance in this case is the excess distance the debris has traveled across the valley beyond that which you would have expected the debris to have traveled if the material had behaved like a frictional material. In this case, the excess travel distance is about 1.45 miles, further than would be expected if the material had acted like a purely frictional material.
The problem is kind of a mechanical paradox, and I think that excites at least a lot of the scientists, because when you have a paradox, that is, when you expect one thing, say on the basis of laboratory measurements, and you find something totally different in the field, it means there's something very new to be understood.
Well, I think the paradox probably caused by the semantic problem. In the Anglo-Saxon country, they call this phenomenon landslide, implying the process is one of sliding a rigid block. But in fact, it's a phenomena, the broken rocks becoming liquid. It's a liquefaction problem. Therefore, if we treat the problem as liquefaction problem, we don't have this paradox.
It's a liquefaction problem with a difference.
The mechanism is cyclotropic flow. And cyclotropic flow is a mechanism, the viscosity is velocity dependent. The greater the velocity, the smaller the viscosity. Therefore, it has feedback mechanism to acceleration is much greater.
But thixotropic flow doesn't quite explain how a landslide can travel. East of Los Angeles in the Mojave Desert is a landslide that's been studied by another lone geologist since the 1960s. It's called the Black Hawk Slide, just a thin smear across the desert. But look closer, and you see an undulating surface, out to a rim that's raised above the flat desert floor. One edge is marked by a thicker line of debris. In 1995, geologist Ron Shreve returned to the outer limit of the landslide he first studied as a student in 1959. He thinks he solved the problem of what caused such landslides before most other geologists even knew they existed.
The slide started at the top of the mountain, there where it's gray. It came down Black Hawk Canyon, dropped about 2,000 feet in a mile and a half. Then it spread out on this gentle slope that we're standing on here. It came 5 miles from there to here. The right-hand side of it overtopped that hill, which is about 200 feet high. That means that it had to be going at least 75 miles an hour to get up over that hill if it did it by its own momentum. The rest of the material was not stopped by the hill. It came right to this point, and we know that it stopped very suddenly because it piled up and formed this rim along the whole front edge of the slide. The front stopped first here, and then the material right behind piled into that and kind of rode up on it, and then the next part behind and so on, like a railroad train where the engineer slams on the brakes on the engine and all the cars pile up one after the other.
From out here on the rim, the place where the flow started doesn't look much higher up.
Okay, that's 6 degrees. Gravity just isn't strong enough to pull them down a slope like this. So there had to be something underneath to reduce the friction. The hypothesis that I have proposed, and I think explains these features the best, is that this landslide slid on a cushion of compressed air. And the way I visualize it is that when the rock fell down off the mountain, it broke up into a kind of a flowing mass of broken rock and debris, which poured down Black Hawk Canyon. And near the mouth of the canyon, there's a ridge across the canyon that was served like a step that caused the slide material to go up over it and down and trap air underneath. And as the slower moving material came behind, then that curtain of material gradually lowered, and that air spread out underneath this landslide lobe as it came forward. So I actually visualize it then as sliding on a layer of air about this thick.
It was only after St. Helens, when more scientists had heard about such landslides, that Ron Shreve's air lubrication theory hit a problem.
This is a volcano on Mars. This poses some real problems for the different theories of long run-out landslides. On the flank of the volcano, you can see a landslide here that extends several hundred kilometers away from the flank. That is one of the larger long run-out landslides by terrestrial standards. However, the broader aureole here of rough terrain has been interpreted by many geologists as a landslide deposit itself. If that's correct, it means that the largest landslide in the solar system is located here on a planet that doesn't have a significant atmosphere, which means that atmospheric pressure probably cannot have played a role in the emplacement of this gigantic deposit, which is half the size of the United States.
That vast landslide is controversial, and Shreve is still confident.
The atmosphere on Mars is very much thinner than on Earth. It's similar to our atmosphere at 100,000 feet. But I've done some calculations, and I just redid them yesterday, which show that the large landslides on Mars for which we have enough data all could have trapped enough air with a present Martian atmosphere to be air layer lubricated with an air layer about this thick.
Many of his colleagues may still not accept this, but they do respect his contribution to landslide theory.
mean, he's the person who inspired the mechanical investigations of these landslides, and everyone who proposes a theory, of course, compares their theory to his. There are probably just about as many ideas as there are investigators. There are at least 20 well-documented theories that have been proposed to try to explain how these landslides move. One of the more exotic ideas was that as sliding occurred, melting would take place at the base of the landslide, and the landslide would essentially ride out over a thin film of melt. Another idea was that as sliding occurred, the heat developed along the base of the landslide, vaporized a bit of water, and it was the pressure of the steam that essentially lifted the rocks above it and allowed the slide to move with very low friction. Most of these ideas originated when an investigator studies a particular landslide. The problem is when you try to apply the theory to some other landslide, it doesn't always work.
So Jay Malosh has a theory of his own.
I think that the essential factor in lubricating the landslides is strong mechanical vibrations in the landslide itself.
He calls it acoustic fluidization and can show how it works with a bucket of sand.
You can see that the sand in this bucket is pretty firm. I have a cylinder buried in here, coated with sandpaper. The cylinder is connected by this rod to a pulley, and the pulley is being twisted by the weight. So the weight is putting a twist on the cylinder at the bottom. It's not going anywhere right now, though, because it's stuck in the sand. If we now turn on the sound, you see that the weight begins to drop as the cylinder rotates. It's as if the sand is turned into a liquid. And if I do the same thing with my fingers now and push them into the sand, they go straight in, all the way to the bottom of the bucket. So the behavior of the vibrated sand is completely different than that of ordinary sand. It acts like a dense liquid.
Which would explain a shape like this blot on the landscape of Alaska. All the rival theories have been collected up by Phil Schaller.
Yeah, well, this one is just crazy.
He wanted to try to arbitrate on them for a doctoral thesis that itself ran out to over 500 pages.
Probably, hopefully. Unfortunately, after you've read a number of these different proposed theories, you find that they're mutually exclusive. So you start asking yourself whether there is the possibility that none of the proposed hypotheses are, in fact, functioning for long run-out landslides at large.
Any theory needs to be tested.
When the Frank slide came down from that mountainside in 1903, it hit the bottom of the valley, and the bottom of the valley at the time was covered with very fine silty sand, a black silty sand. In this particular case, we were exploring the hypothesis that this material was liquefied by the impact of the material on the valley bottom. And it's because of this that we'll be taking samples, hopefully, from beneath the debris, which we can test later on in the laboratory.
To reach the layer it was sliding on, they had to drive down through 30 feet of the limestone.
This is a joint project or a joint idea. The idea, however, began with Professor Sasa at Kyoto University in Japan, and he and I are working together on the Frank slide as a possible example of this mechanism of long run-out landslide motion.
In Japan, 100,000 landslides of all sizes have been classified as being on dangerous slopes. Many are close to towns or cities. Perhaps because Japan is the country where this ever-present threat is taken most seriously, it has a disaster prediction research institute. And the world's only scientific journal of landslide news, edited by Kyoji Sasa. In this one country, they have a nightmare range of different kinds of landslide. This is what most people might expect a typical landslide to look like. It continued slowly on and off for several days. Plenty of time for a television crew to get here. It was a disaster for the people who live in this small town. But in this case, it was neither big enough, nor high, nor steep enough to gather any speed. It's what they call a slump. The run-out is contained. Other slides are vastly more impressive. One comes from a volcano maybe 20 times a year. For safety, Japanese engineers managed to channel the debris flow. To catch it on film, they strung a piano wire across its path, which turned on a camera when it broke. It may look like flowing water, but it's mostly rock. Even this is a pale shadow of the fury that nature can unleash. Kyoto, Japan is one of the few places in the world where the material from landslides is collected for experiments. They have samples from the Americas, China and Iran, though mostly from all over Japan. They also have the samples from the Frank slide in Canada. They believe they can predict future disasters only by knowing what's happened in the past. When the sample is fully saturated, it's put under pressure and twisted to simulate conditions in the early stages of a landslide. As though in slow motion compared to the real thing, this boundary layer is crushed, then gradually reduced to a fine watery slush, at which stage it suddenly gives in the same way as a long run-out landslide begins.
長距離運動地滑りの最も重要な原因は水だと思います。地滑り土塊が運動してきたときに飽和した層が地面の下にありますと、地滑り土塊が乗ることによって土の層は圧縮されますけども、水は圧縮されないので間隙水圧が発生します。でもう一つは旋断が起こることによって粒子が細かく砕けます。で砕けることによって間隙水がさらに発生します。したがって地滑りが動くときには高い間隙水が発生しますので、結果として非常に低い摩擦係数が生じます。で今回の実験、この実験で起こった計測しました摩擦角はもう 2.9 度しかない非常に小さな摩擦角が得られています。
But Kyoji Sasa's theory always requires water.
There we go.
Which prompts a familiar criticism. At Caltech, they've enhanced pictures of more Martian slides.
Well, the sun is coming from this side, right down here.
These seem much like landslides on Earth, allowing for the greater heights and distances in the lower gravity.
And the long run-out landslide extending out into the bottom of the crater.
But Martian landslides are not seen as a problem by Sasa.
特に問題があるとは思いません。火星にはかつて水があった可能性がありますし、現在でも凍った状態の地下水がある可能性があります。
But again, others aren't easy with this idea.
Well, it does make for a somewhat uncomfortable situation because all of these workers have done a lot of work to support their various theories. Unfortunately, when you come up against a situation where two theories or 3 or 4 or 12 don't agree on the details, you have to sit back and look critically at the hypotheses and the assumptions that have been made to support the hypotheses.
In a suburb of Melbourne, Australia, they seem to have a winner. This simulation needs no water. Paul Cleary put an American idea on how landslides can run with nothing more than rock into a computer at the Australian Commonwealth Scientific and Industrial Research Organisation.
You've got a triangular cliff on there, and that triangular cliff has been broken by an earthquake or some such cataclysmic event into a whole lot of 1.5 metre diameter boulders. The shape of the landslide becomes rounded and can reach speeds of hundreds of kilometres an hour by the time it gets to the bottom of the valley floor. So despite it being millions of tonnes of rocks, it actually looks very much like a liquid flowing over and the wave breaking. The initial strata, the green and the blue at the top, are preserved. They're a little bit clumpy. The bigger the landslide is, the smaller the proportion of material that's colliding, so the lower the effective friction is and the longer the landslide will run out. And for very, very large landslides, the distance run out by the landslide could be 20 times the initial distance that the landslide fell.
The crucial question is, what does it tell them about the mechanism?
What you're seeing here is a segment of a very small long run out landslide after it's reached the valley floor. You can see a rough bottom boundary, and the landslide, which is moving very, very fast over the ground, collides with the bottom boundary. The collisions between the particles form a very, very dilute shear zone, and it lifts up the entire landslide. You can see that most of the landslide is actually moving as a solid mass. It's almost a passenger. It just rides down on top. It supplies energy to the flow at the bottom. And that's really the secret of why a landslide can go a lot further than traditionally was thought. The cause of the controversy, I guess, has been solved. Just the particles rolling over each other in itself is entirely sufficient to explain why the landslides run out a long distance.
The ultimate proof of any theory would be to create a long run-out landslide and watch what happens. And this is the closest anyone has ever got to that. In Kazakhstan, scientists triggered a debris flow, which went on and on for 2 hours. What can be seen is rock debris, with rock dust thrown up. As it drove large boulders before it, the debris flow seemed powerful enough, but the energy released over 2 hours was almost nothing compared to that delivered by the Frank slide in just 100 seconds. And that in turn was tiny compared with the awesome power of the landslides of Hawaii. These are some of the largest yet discovered on the planet. Deep under the waters of the Pacific, those runaway mountains swept vast blocks, one the size of Manhattan, across the ocean bed. This is a process that's been going on for many millions of years, as volcanoes grew and then collapsed. Just over 2 million years ago, this cycle reached Oahu and Molokai, and has now crossed the Big Island. Here, the energy still being delivered into that system is mostly hidden underground. Cutting round this volcanic region is a rift over 60 miles long. The southern end is called the Great Crack. To one side of this Great Crack lie 200 square miles of the Big Island of Hawaii. The big question now is not whether there'll be a landslide, but how big. and when. The volcanologists know that at the lowest end of the scale, there's a small earthquake about every 10 years, and movements big enough to make a small tidal wave, a tsunami, about once every 100 years. But they can't yet predict when or where the next will open up. Roger Denlinger came here in 1991 to see if he could find out what's really going on beneath his feet. What the mechanism is that generates all these cracks.
The sides of this crack fit together like the sides of a jigsaw puzzle. It is the largest crack and the last one between here and the sea.
In order to explain all this, he needed to survey the whole south flank of the island very accurately, time and time again, to see how it changed. The equipment available at the start of this investigation was a laser ranger. Accurate to a few millimeters, it calculates the distance from the speed of light itself. But on Hawaii, they had no fixed reference point. They could see that distances were changing, but couldn't tell what was moving and what was standing still. So they had to start again and put in a completely new system called GPS, the satellite-based global positioning system, originally developed for the US military, which gives precise positions anywhere on Earth. The volcanologists can now pinpoint their readings, again to within a few millimeters, across the whole active shifting south flank.
What we did was we set up an experiment to see if the flank was moving at a steady rate, which people had believed. And we found in 1994 that the flank actually stopped and then started up again. And not only that, but it stopped for 4 months during a period when the pressure in the magma system dropped.
But as the pressure rose, it started moving again. And in response to that pressure, the whole of the south flank is currently moving as a single piece and floating on a vast chamber of molten rock below.
Well, I think the results have been really exciting, and they were starting to finally be able to really tie together what the magma system is doing with what the flanks of the volcano are doing. I think it's the key thing that's really coming out of all this is that these giant landslides around the islands are almost certainly driven by the active magmatic system inside the volcanoes.
The next landslide and the next tsunami will be triggered by the volcanoes right here. The volcanologists monitor the pressure of the magma and collect samples to see how it changes. But right now they have no way to predict whether the next event will be just another small earthquake or something big. Jim Moore hopes they can discover some reliable warning sign.
We've just been out on the east rift of Kilauea volcano. The rift zone is a zone of tension, which is a pull apart between the mobile south flank of the volcano and the more stable northern part of the volcano and the rest of the island. It's moving south at a rate of something like 10 centimeters a year. At the present time, there is about 400,000 cubic meters per day of lava issuing from it.
Over 1 million tons a day. That's enough for a Swiss landslide every week. A Frank slide in less than 3 months.
When you realize that the 1975 earthquake landslide, which only moved 10 meters, caused damage in Southern California, it's evident that a major movement of this kind would certainly be felt completely around the Pacific Basin. It's anybody's guess when the next one will occur.
When it does, it would hit the coastlines of America, Japan, and again Australia. But the Australians have now discovered more recent underwater landslides on the edge of their own continental shelf.
I think we really are looking at 2 major tsunamis. One from the northeast to cut the highs, and one then coming up from the south, washing the boulders over these big rock walls and dumping them up in here.
Offshore, there's been no good survey of what else might be out there waiting to happen. but they spotted some oyster shells embedded in a rock, which they used for carbon-14 dating. It told them the earliest time it could have been swept up by tsunami. And this lot's very recent.
We can see your northeasterly one carving these out. Then we've got a major, at least this major event coming up from the southeast and bringing the boulders up. Now, the C14 age we've got for that is what, 700? 800 for this one. But what we can also see right along the coast from, in fact, Victorian border to Sydney, is yet a third event in which the C14 ages are all modern, within about, say, just before white settlement.
Underwater landslides from the edge of a continental shelf can cause a great wave, a tsunami, in any ocean of the world. But some of the biggest come from the runaway volcanoes of Hawaii. Here on the Big Island, the balance of the south flank is changing. Every day, 1 million tons of new rock is dumped along the seaward edge, twisting and pulling this side down. It could slip a little in a slump, or it could all go. The giant runout that sent a wave to New South Wales was big. But if the next breaks off here at the Great Crack, this one will be 10 times bigger. If the whole south flank broke free, moving as a single piece, that's half a mountain. But we know that half mountains can run away.
Well, if we are unlucky to be around for one of the really large events, a significant part of the south flank of Kilauea will slide into the ocean and generate an enormous tsunami. There would be a series of large earthquakes, presumably in the magnitude 7 to magnitude 8 range, probably many dozens of them as the slide continued to move. And it would be the catastrophe of civilization.
Volcanoes and earthquakes are the focus of the first Royal Institution Christmas lecture on Wednesday the 27th of December here on BBC Two.